Okay. So first I want to say thank you for being flexible with having to do a makeup session. So we'll have one next Thursday. Serpo was thinking that why on Valentine? We have to celebrate proteins on Valentine? Well, yeah. So think protein on Valentine's Day. So basically I'll continue and then we'll have a lecture like regular next Wednesday and another one on Thursday. I sent an invite we'll have it in room 23, so in our building. So I put that in the Google invite. So that's that. What else I wanted to say? We have established all of the presentation topics in groups, so these were selected. We have Nina and Becky will go April 3rd, and then Lucy and Vaidehi will go April 10th, then Rachel and Jason April 17th, and Lisa and Katie May 1st. Okay, now we have a new student. You have Fan. Hi, Fan. Now you're the odd number. So we usually have groups of 2 for a presentation. So you have a choice to present on your own a topic. I'll come up with a topic for you. Or you join one of the groups and I'll have to think which topic can be expanded to 3 members. What is your preference? You can think about it and tell me later. Okay, and then I will consult with other group members to see who will take on another person. Okay, so with that, let's try to remember a little bit what we talked about 2 weeks ago. Oh gosh, I also forgot where I even stopped. I kept trying to remember which slide I was on. Couldn't remember. But anyway, you guys are going to help me out. So what I plan to do a little bit different, not very different than previous years, is every time I have recap questions. So this is not new for me. But what I usually I have practice sets for a lot of topics. So instead of having you do the practice set on your own and then look at the key later on, what I will do is incorporate, since it's 2 hours long class, it's really boring just for me to talk at you. So what I thought we will do, hi Jason. What I thought we can do is every session we kind of have a 20 minutes of breakout discussion. So I can divide you into groups of 2 or 3, and then what you can do is you look at the practice problems and discuss it amongst your group of 2 or 3, and then we can discuss your answers to the group of the class. And then after that, you take your time, a week, to write all the answers down and submit it for extra 5 points. Okay? So this is what I'm going to do differently. This way I ensure that all of you have thought about the questions and all of you got the answers correctly by discussion rather than just reading my key online. Okay? And this will break the 2 hours of just lecturing. I know I get bored, you get bored, get tired. So yeah, that's something I thought we should try this year. Okay, so trying to recap a little bit. Can anybody remember some nutritional and physiological roles of proteins?
Build muscles.
Build muscles, yeah. Definitely. So protein is important for muscle building. That's great for athletes. And regeneration of muscles, if we lose them, with aging as well, is helpful. Consumption of protein for aging is also a good thing. All right, what other than that? What did we talk about possible physiological benefits of protein? Bioactive peptides, which can be generated as we ingest the protein by random digestion. We can release some peptides that will have bioactivity, or we can produce hydrolysates outside of the body and then use them in food products, and these could have some biological activity. Of course, from a nutritional standpoint, we need a certain amount of essential amino acid and a certain amount of protein daily for our nutrient requirements. Okay, what are some physical roles of proteins in food? Gelation. So structure, basically. Impact of protein on the structure of the food. So it could be, structure could be in the form of a gel, a foam, an emulsion. What other than a structure you can have, Lisa?
Water binding.
Water binding, which is, yes, water binding is important. For example, in a sausage application, water binding and water holding become important because you don't want to have syneresis of your product, or a beef patty, for example. When you cook it, you don't want to have syneresis and you lose some of that. Let me finish the thought. Some of that weight. Because sometimes when people produce beef patties, for example, they care about the weight because the weight is related to the cost. So if you lose water, you are losing free money, basically. So binding of the water, making sure it's in there, not just water, but fat as well. Binding of the fat in a system that is high in water and high in fat will also be very beneficial.
I was going to say emulsions, but that kind of applies to the sausage too, because it's binding both water and fat.
Yes. So emulsion, sausage is one application, salad dressing is another application, ice cream is an emulsion. Other than that, other than structure, we talked about other things. Color. Color is one. So casein, for example, in cheese is what's giving the white color. Maillard reaction gives the browning, and sometimes it's desirable and sometimes it's not desirable. Polyphenol oxidase is an enzyme, it's a protein, will also produces brown color. In some applications is not desirable, like in fruits and vegetables. More than 40% of the produce are lost due to browning from polyphenol oxidase. Sometimes it's desirable, like in tea, for example. Fan, what did you want to say?
The flavor, like hydrophobic amino acid, has flavor taste.
Yes, so the flavor and taste. So flavor and taste, basically we're talking about either hydrophobic amino acids. So if we have high percentage of hydrophobic amino acids, and then you break those proteins into peptides that are high in hydrophobic amino acid, then you start tasting bitter. Or if you have high percentage of acidic amino acid, you taste sour. High percentage of sulfide group, you taste the sulfur, like in egg. So, what are some intrinsic factors that impact protein structure? Nina? Hydrophobicity. So the hydrophobicity, which could be an intrinsic factor because it's based on amino acid composition. So when we say amino acid composition, it impacts hydrophobicity, it impacts charge of the protein, it impacts the structure of the protein. So under intrinsic factors, you have the amino acid composition, you have the amino acid sequence, not only how much of a particular amino acid you have, where it comes in a sequence, dictates what kind of intermolecular interactions you're going to get within the protein and across different proteins. What about extrinsic factors? There are many extrinsic factors. Go ahead, Becky.
The pH of the solution the protein is in.
The pH of the solution, yes. So the environment is one, huh?
Modification.
Modification, very good. So we can modify the protein by enzymes, by chemical, by heat. Yes, Lucy?
Temperature.
Yes. Temperature modification. So if we are drying or pasteurizing or removing a solvent, so all application of heat will impact the structure of the protein. So we talked about pH, heat, modification, storage conditions, thank you very much. Presence of salt, for example, in the environment. So many extrinsic factors, they will have several impact on the structure, and we'll talk about all of that this semester. Okay. Can you give an example? I don't know if I got to do that last time or we ended earlier, but can you think of examples where if we did something processing or drying or whatever, and a protein structure was impacted, how would that impact functionality? Can you think of an example? If I didn't mention it last time, that's okay, let's think together. Which of the extrinsic factors may impart what structural change and how would that impact functionality? You had your hand up.
If you take a globular protein and make it a more open structure, doesn't it become a better polymer or emulsifier or something like that?
Yeah, yes. And how do we open up the protein? We can do that by mild thermal denaturation. So we can denature the protein, unfold it a little bit so that it can emulsify better or foam better or even gel, because many of the gel systems in the food industry is thermally induced gels. Of course, there's the cold set gels that are impacted by pH, but many of the applications involve thermally induced gels. On the other hand, some denaturation or extreme heat treatment can cause denaturation and polymerization and negatively impact the functionality. Can you think of one functionality? Huh? Yes, she's thinking from nutritional side of view, yes. So when you polymerize the protein, you have less digestibility, and that will impact bioavailability. I was thinking more of a functional outside of the body. So if you're producing a beverage high in protein, and then you thermally processed it and it sat on the bench, what do you expect is going to happen?
Poor solubility.
Poor solubility. So over time, your protein can polymerize, precipitate, and then your shelf life of the beverage will be shorter. Okay, we'll have many other examples, obviously, but what is the R group on an amino acid and how it may differ among different amino acids? Yes, Jason?
Well, I mean, it's good fairly to diversify the protein, or sorry, the amino acid, so it's based upon the structure of the R group, we're going to change that.
Yes, diversify the amino acid based on the structure of the R group. We're going to talk about the R groups for all the different amino acids and how they differ in functional groups. Today, how they differ in reactivity because of the different functional group, and that impacts structure of the protein, impact the reaction of the protein with other proteins, with sugar, with water, with etc. So the R group is really the heart of your protein, basically. It dictates structure, it dictates function. Okay. So this is kind of our roadmap that I've showed you last time, showing how intrinsic factors impact structure. We're going to talk about all of that, how that impacts structure, and then how we go from native to denatured or modified by extrinsic factors. How would that impact structure? How will it impact functionality? All right, so this is kind of our roadmap that I will be bringing up a lot during the semester, and then it will help us see where we're at. Okay, so I think I started with intrinsic factors last time. This is where I forgot where I stopped. But I think I started with, I told you we'll talk about protein sources later, but we're going to talk about all the intrinsic factors first and how they impact protein structure. There are so many different proteins in nature, and all of them are different. Even within one source, you have multiple protein subunits and peptides and polymers within one source. And how they differ in amino acid composition. That's the first thing. Then, not only composition, we said sequence as well. And by doing so, by being different in amino acid composition and sequence, please add sequence to that, it will impact structural configuration. By structural configuration, we have different level of protein structural configuration, which we'll talk about hopefully today. We start with primary structure, secondary, tertiary, and quaternary. So the primary structure is basically your sequence of amino acid, and then whatever the sequence is, it will dictate secondary structure, and then how tertiary structure is formed, and also quaternary structure. Chemical and biochemical properties, that is also directly related to amino acid composition. So hydrophobicity, so the higher you might have really high percentage of hydrophobic amino acid, like corn protein, for example, is really high in hydrophobic amino acid, whereas whey protein is not. Also, the amino acid composition dictate net charge at a particular pH. Some proteins have net charge at neutral pH, other proteins barely have any charge at neutral pH. For example, basic proteins, such as pennycress and camelina protein, oh dear me, they're very basic, they won't be solubilized or have charge unless the pH is 11 or higher. So that is characteristic of the composition of the amino acid within the protein. And hydrophobicity is also not only total hydrophobicity. What's important is where the location of the hydrophobicity is. How many pouches do we have of hydrophobic residues? Are they clustered together or are they scattered across the polypeptide chain? If you have clusters, that helps with emulsification properties, for example. Then you can have a really hydrophilic end and a hydrophobic end, such as, for example, casein. So that's why we call casein is a natural emulsifier. All right. So because different proteins vary in these intrinsic factors, they vary in functional contributions, obviously, and we'll see how. Okay. So stepping back into basic chemistry structures of amino acids. I know you've seen this many times over the years in different chemistry courses and food chemistry, but here I want to relate it to the protein, their structure, and their function in food. So that's why I'm going to step back and have you know all the structures of amino acids. Don't hate me for that. You will know why later on, why this is important. Okay, so I don't know, did I talk about this slide last time? Did I explain the acidic and basic functions? Okay, so we have a chiral carbon. It's called C alpha is chiral because it has a different unit or functional group attached at each bond. So it's called, that's why it's chiral. And it is L configuration because the amine group is on the left. All right. So at neutral pH, the amine, the primary amine and the carboxyl groups attached to the alpha carbon will be ionized, and in that form, they act as a base and they act as an acid. And that's why it's an excellent buffer. And I don't know if I gave you the example of acidic beverage last time. Did I? I did? Okay, so I won't repeat myself. All right, so they buffer as the pH, as you try to change the pH by acid or base, they will resist the change in the pH. Because the basic group will tend to capture protons, and the acidic groups will tend to give you your protons. But the acidic group, as you titrate with an acid, eventually it will pick up hydrogen or protons, and as you titrate with base, eventually your amine group is going to give up its proton. Okay, but as I said, the most important group is your R group because it determines, due to different functional groups, it determines the polarity. So long chain will be nonpolar, or if you have an amine group, potentially positively charged. If you have additional carboxyl group, that will be negative charge. Hydrophobicity, structure, we'll talk about that in detail. Reactions and interactions due to the functional groups on the R group. And obviously function out. So we're going to look at each amino acid together, or each group of amino acids. So we'll start with the nonpolar or the hydrophobic groups, and they're divided into two. We have the hydrophobic that are aromatic, and we have the hydrophobic that are non-aromatic or chain aliphatic. So, so the aromatic groups, we have three of them: tyrosine, tryptophan, and phenylalanine. So they all absorb light in the UV region. 280 nanometer is that region in the UV range. And that's why every protein can absorb UV light, because every protein has a certain percentage of tyrosine, tryptophan, and phenylalanine. That's why protein in a purified solution can be quantitated using UV absorption. So the main amino acids that have the most absorptivity is tryptophan. So tryptophan has a molar extension of 5,500. So it's the main one that absorbs in the UV range, followed by tyrosine. The least light sensitive is phenylalanine. An important characteristic of tyrosine, similar to another amino acid that I will point out later, it ionizes, the hydroxyl group ionizes at alkaline pH. Keep that in mind when we look at, for example, solubility of soy protein. We'll notice that its solubility will be higher at alkaline than at acidic conditions. And one of the reasons is the ionization of hydroxyl groups and sulfhydryl groups. So you want to keep also in mind that the higher net charge, the more soluble is the protein. So when one functional group ionizes, that means it carries a charge. That means its solubility is enhanced. Okay. The aliphatic groups, they're really boring. They don't do much, really. Other than some of them are essential amino acids. But really they don't have much of reactive group. They're a bunch of methyl groups. And then one interesting one is proline. And the reason I say it's interesting, because look at its R group. So you have three methyl groups, but the last methyl group is actually bonded to your amine group. So with this being bonded, then you don't have much flexibility in the bonds. So you don't have much of a turn and stretch of the bond. How is this relevant? It is relevant because when we talk about secondary structure and tertiary structure, whenever we have high concentration of proline, you no longer have a secondary structure. It doesn't form. It forms mostly random coil. So caseins, for example, are high in proline, and therefore they don't have much of a secondary structure. So it is a secondary structure breaker because of the rigidity of the R group. There is another form of proline, which is hydroxyproline. It is present in collagen in meat, and it's actually a post-translational modification of proline. Two other points to mention is methionine as a sulfur group, and which is unique from others. And then another thing is the beta carbon, which is the carbon attached to the alpha carbon, is also chiral. That means every bond is different. That's the only thing that is unique here. Talked about proline. So moving into the hydrophilic, there is the polar that are charged, and then the hydrophilic polar that are not charged. So we have 5 amino acids that carry charge. So we have the histidine, lysine, and arginine. These are all basic amino acids, so they carry positive charge at neutral pH. We also have, again, collagen, under post-translation modification, we get hydroxylysine as well. Negatively charged amino acids are the glutamic acid and the aspartic acid. So in this case, we have, in each amino acid, we have 3 pKa's. We have the acidic pKa, basic pKa, so pKa1, pKa2, and then pKa3. One thing I want to point out, if in each of these different amino acids, you'll see that lysine, for example, has a primary amine. That means the amine have one bond with carbon and the rest is hydrogen. And the primary amine is the most reactive amine group, especially in the Maillard reaction. And that's why when we talk about Maillard reaction, they talk about lysine loss, because it's the most reactive amino acid because of that primary amine. In arginine, you have secondary amine, so the amine group has 2 bonds with carbon. And then in histidine, you have a tertiary amine, which has 3 bonds with carbon. Okay? This histidine is the least reactive in Maillard reaction. So this is what I was talking about. So you have a Maillard reaction of the reducing sugar, so the carbonyl carbon from the reducing sugar, which you all know, we learned about in food chemistry, reacts with the primary amine. And that leads to nutritional loss, basically. That's one of the disadvantages in processing. When we thermally treat proteins in the presence of reducing sugar, we have a tendency to lose lysine. So the polar hydrophilic that are not charged, we have serine and threonine. Glycine is a very unique amino acid since it's the smallest amino acid. Your R group is only H, and it's non-chiral. This alpha, C alpha is non-chiral because you have 2 H groups. So this is a very unique amino acid, the smallest, and that will have the most flexibility in rotation of bonds in a peptide bond. So remember that, because it's small and there is barely any sterical hindrance due to very small R group, which is the H. Glutamine and asparagine, these under acidic and alkaline conditions, you lose an amine group. So this amine group here is lost, and this one is lost, and you end up with a carboxyl group. This will give you glutamic acid and aspartic acid. So serine and threonine are also important amino acids because of the presence of a hydroxyl group in each one of them. So what is the role of this hydroxyl group? It has a post-translational role. A lot of proteins are conjugated in nature. That means they're not amino acid, not homogeneous. They are heterogeneous. That means you have amino acid and also you have additional groups. In this case, in caseins, you have alpha and beta, you have phosphorylated proteins. And we'll talk about them when we talk about the dairy proteins. So, and phosphorylation of the casein plays a major role in the stabilization of the casein micelle. Okay, so what is the location of phosphorylation? The location is on serine and threonine. So many groups of serine and threonine in the alpha and beta caseins are phosphorylated to give you this structure here. Kappa casein is another form of casein that is glycosylated. And also glycosylation is a post-translational modification at the OH group of serine or threonine. So you have acetylglucosamine that can conjugate to the protein. So, and that gives you this particular structure, a glycosylated protein. The glycosylated protein also plays a very important part in micelle stabilization. So this, it will come back again to us, but I'm just going to, where did we find it last time? So the micelle is in milk. You have casein micelles stabilized, and they stay as a stable system. They do not precipitate in milk. Why? Because you have at the edge or at the surface of the casein micelle, you have the glycosylated kappa casein. So the glycosylated end of kappa casein. So this keeps it very polar and interacting with water on the surface. So that this micelle and this micelle will not come together and coagulate. Within the micelle in here, you have all of the phosphate bridges with calcium, forming calcium phosphate bridges, which keeps everything together inside of the micelle with the kappa casein outside of the micelle because of the glycosylation and phosphorylation. We'll talk more about the structure later when we talk about casein, but I just want you to visually see the impact of phosphate groups and glycosylated kappa casein groups at the surface, and that's what keeps the casein from precipitating out of milk. Another important amino acid is the cysteine. The cysteine is important because it has the sulfidyl group or thiol group. It's a very reactive group which imparts S linkages. So oxidation leads to the formation of a bond, a sulfide or disulfide bond between two cysteines to give you a cysteine. And you can pronounce it a little differently. You can stress the EI here, and here you don't stress the E. There's no E. That's the only way to differentiate between a single cysteine and a cysteine. All right, so what the importance of this is within one protein, it stabilizes the protein structure. So if you have a protein with high disulfide linkages, it resists thermal denaturation. Okay. Also, if you have a protein with high free sulfidyl groups and you induce oxidation through processing or denaturation by physical means of denaturation, as in the kneading of the dough, for instance. So when you have water and flour and you start kneading your dough, you're denaturing the protein. And when you're doing that, you're opening up the structure of the protein, and the protein starts interacting via hydrogen bonding and disulfide linkages, forming the gluten network. So disulfide interchange plays a lot of different roles in food system. One, stabilizing the protein itself. Two, generating matrices that are stable for different applications. And three, can cause polymerization, which is in some cases, such as solubility, not desirable. Another reaction of certain amino acids is important in food application is, for example, you want to produce bread from rice flour, and rice proteins do not polymerize as good as gluten proteins. So if you want to induce the polymerization, you can add transglutaminase enzyme, and that transglutaminase enzyme link the amine group of a lysine residue, this one here, an amine group of a lysine residue, with a carboxyamide group. So the amide group that is linked to a carboxy group in a glutamine residue. So in presence of the transglutaminase, a covalent bond is generated and an amine group is released. Okay, any questions? All right, I'm going to switch topics slightly. Talking about the acid-base properties of amino acids. Here I'm going to talk about pKa and pi, which are very important characteristics. pKa is related to the amount of ionization, and pi is when you lose the pH at which you don't have any charge. So when we process proteins at the isoelectric point, we're basically causing more denaturation to occur and polymerization to happen. So when we process or treat a protein or dry a protein, you don't want to be at the isoelectric point. Because at the isoelectric point, you don't have any repulsion between the proteins. So they will come together and interact and form polymers. So what happens when you don't have charge, the hydrophobic groups on the surface of the proteins now can come together. There's nothing to repel them because you have neutral charge. So they come together, and as you are, or as they come together in a close proximity, other interactions can happen. Hydrogen bonding, ionic interactions, covalent linkages, any type of interaction, obviously hydrophobic interactions. So when that happens, we are losing the functionality of the protein. So isoelectric point is very important, but you can reverse it. So for example, if we are extracting a protein, sometimes we solubilize it first at a particular pH, then to separate it from other solubles, we bring the pH to its isoelectric point. So, but we don't leave it there. Once it's precipitated and separated from other solubles, we neutralize it again. So it is reversible. So isoelectric point is very important. pKa, again, it has to do with the charge of your protein. So we have pKa for the carboxyl groups and pKa for the amine group. So if we look at one amino acid, which is serine, pKa equal 2.21 for the carboxyl groups. At pH below 2.21, most of your carboxyl groups become protonated, so you lose a negative charge. At pKa above 2.21, you start getting more of the negatively charged carboxyl groups. You lose the proton. So above the pKa, they're mostly negatively charged. Below the pKa, they're mostly neutral charged, the carboxyl group. Okay? At the pKa itself, half of the groups are protonated, half of the groups are ionized. That's the pKa, which is the pH at which you have 50% dissociated and 50% non-dissociated. You'll notice that the pKa for the amine group is high, because it's basic. Okay? The amine group is not going to give you its hydrogen or proton very easily. It needs to be really basic conditions for it to give up its proton. So, in this case, pKa below 9.5, your amine group retains its proton. It's positively charged in this case. Above pKa 9.15, it's mostly giving up its proton and it's neutral, not charged. So if we're thinking about a protein, then it would be the net charge will be negative as you increase the pH. And as you decrease the pH, the net charge will be positive. right? Do you want me to repeat? I'm happy to repeat.
Please.
Yes. Okay, so at pH 2, okay, think of a pH 2 and look at this. What's the charge on this amino acid?
Positive.
Positive. At pH 10, what's the charge here? Negative. So when we decrease the pH, you are most likely generating a net positive charge, because this one is holding on to its proton. It's not going to give it up. It's a basic group. And this, because it's so acidic now, it gets protonated. So it's no longer carrying a negative charge, so the net charge is positive. When you increase the pH, this is going to give you its proton. This is already giving you its proton. It's a strong acid. So now you have a net negative charge. So always think about it that way. Low pH, your protein most likely is positively charged, and high pH, your protein is most likely negatively charged. Okay. With PI, you can calculate easily the isoelectric point of amino acid, but it's not as easy for a protein that is composed of so many different amino acids. There is an equation, you can learn it in a chemistry course, I'm not teaching it. So, but the idea here in an amino acid, the pKa1 plus pKa2 over 2 gives you the isoelectric point, which is the pH at which you have neutral charge. If we think about it for a protein, again, above the pi, your protein starts to become negatively charged. Starts, not necessarily all of it is negatively charged. And at below the pi, your protein starts to be positively charged. So the net charge will be positive below the pi and negative above the pi. All right, so, but an amino acid is not that simple. Sometimes you have a third pKa, which is the side chain. We have 3 basic amino acids and 2 acidic amino acids. That mean we have a third pKa. So if you look here, arginine, histidine, not very basic, but lysine. So if we look at arginine and lysine, you see that the pKa is relatively high. So for them to give you a proton, the pH really needs to be high. But the pKa for aspartic acid and glutamic acid is mostly acidic. So they are readily going to give you their proton below at the pKa of 3.6, for example. Half of the aspartic acid will be positively charged and negatively charged, and half of it would be a neutral. So in case of calculating isoelectric point for acidic or basic, in this case you take pKa1 and pKa3 for acidic by 2, whereas for basic, the amine group pKa2 and the amine group pKa3 by 2. So this is for amino acid only. As I said, the calculation for a protein is different. And here is just to remind you, if you remember the Henderson-Hasselbalch equation, which we learned in food analysis and also in chemical reactions. When the pH equals the pKa, that means the concentration of conjugate base or dissociated equal the concentration of the non-dissociated acid. Okay? So when you have equal concentration, that means log of 1 is 0. And that's when you have maximum buffering capacity. That's when the pH equals the pKa. That means half of your ionizable groups are ionized and half of them are not ionized. All right. And again, here it's a graph that illustrates what I talked about the pH. and negative versus positive. At the isoelectric point, if we titrate with the base, so that means we're adding base, here what's happening is gradually the amine group is going to give up a proton. Then you end up with a negative charge. Whereas below the isoelectric point, as you titrate with an acid, you're giving protons to the system. Gradually, your carboxyl groups are going to be protonated, then you end up with a positive charge. So that is a figure that illustrates above the pi, below the pi, what you expect the charge of your protein to be. Okay? Feel free to interrupt me really with questions. It will give me a break too from talking. Because one of you will ask a question and another will answer it. No? All right.
I have a question.
Sure.
When you mentioned oxidation, can you go and get the slide?
Here. Okay. So the removal of hydrogen here and hydrogen here and formation of a bond, this is basically an oxidation reaction. And then you can reduce it by adding a reducing agent. So basically you break that bond and then give this an H and give that an H. So in the presence of oxygen and alkaline condition, you can induce this reaction. So when you're kneading the dough, for instance, there is oxygen that you are incorporating. Yeah. Mm-hmm. Okay. All right, so other than acid-base properties, we have hydrophobic properties of amino acids that impact different things. All of the above. We're going to talk explicitly how hydrophobic properties of amino acids impact the structure of the protein. We'll get to that. We have several slides on this. Obviously, fat binding properties. The higher the hydrophobic residues, pouches you have, the more tendency to bind to fat. And the higher hydrophobicity, the lower is the solubility. All right. What about this one? Yes, you don't necessarily know this, but yes, Lisa. No, not G. Disulfide linkages stabilizes the protein tertiary structure. We'll talk about that. So, not secondary structure. What? So A and C. The hydrophobic interactions are the main forces driving the formation of protein secondary structure. And I will, like I said, I will spend few slides on this, explaining this phenomena. Hydrogen bonding are indeed the main interactions in the secondary structure of the protein, mainly alpha helix and beta sheet. Again, we'll talk about the different bonding. All right. So, hydrophobic properties. So we have hydrophobic amino acids and we have hydrophilic amino acids. And hydrophobic amino acids basically don't like water. They're hydrophobes. They don't like water. So, right, Rachel?
Yeah.
Are you calling me a hydrophobe? Remember your joke?
I don't remember.
In your presentation.
Oh, I do now, yeah.
Okay. So, that means they don't like water. So when you're forming a protein in a cell, so basically at the end of the formation of the protein is in an aqueous system. It's an aqueous, so there's water. And hydrophobic, that means they don't like interaction with water. They want to interact with another hydrophobic entity. So what they end up doing is coming together, interacting with each other, and the hydrophilic residues will orient themselves to the surface of the protein, okay? So that they can interact with water. So in general, most of the hydrophobic residues are on the surface, most of the hydrophilic residues are, most of the hydrophobic are in the center, and most of the hydrophilic are on the surface. That is kind of the general situation. You all like delta G, don't you? So, hydrophobicity of amino acid is determined by the side chain because every amino acid has a carboxyl group, amine group, and alpha carbon. The rest is the R chain. So whatever is the R chain determines whether the R chain is going to interact mostly with an organic solvent or like to interact more with water. So basically the chemical potential here of interaction of amino acid with organic solvent minus the chemical potential of interaction with water gives you the change in free energy from ethanol to water. If it is positive, then it's hydrophobic. That means it likes to interact more in organic solvent. So its chemical potential of interaction is higher with organic solvent than with water. It would be negative if it is hydrophilic. Okay, but we have an exception. Everything has an exception, which is lysine. Why is that? Because look at the lysine chain. You have 4 methyl groups. So these methyl groups actually like to interact more with the solvent. So for lysine, although it's a polar amino acid, it has a positive delta G. In a protein, though, lysine will orient its amine group to the surface while the rest of it is inside. That's what unique about lysine. And that's why in a protein, when you have heat and reducing sugar, you can still get to that amine group and block it. Okay? So we can actually calculate the delta G of a side chain by looking at an amino acid here. If we look at this amino acid, this looks like a part of glycine, right? And this is your propyl group in a valine, for example. So if I want to determine the side chain hydrophobicity, what I can do is I can get the hydrophobicity or the change in free energy of glycine and the change in free energy of valine. And if I subtract those, I can get the side chain delta G of side chain. So that means calculating it by dissolving, reacting with organic solvent into water, determining the chemical potential. But what I want you to know from this slide is that the side chain determines the hydrophobicity. Okay? And the positive is hydrophobic, negative is hydrophilic. Okay, these are the main points. And another main point is that lysine is an exception. It gives you a positive delta G, and the amine group is on the surface. So these are my main points that I want you to know here. All right, may I give you 5 minutes break? Okay. Lucy, do you know if there is a water fountain somewhere?
Yeah, there's one of our stairs.
I just put it this.
So maybe I can get out of here.
Yeah.
For the UV, they're all absorbent UV proteins.
All of them have certain special concentration of those.
Okay, but it's not because they're aromatic. Only those two are aromatic.
Only those two are aromatic, but because they are present in all proteins, they're called proteins of them too.
What those
Those
components?
three
Okay.
elements that are present in
Oh, okay.
so that's what all proteins are. So it's not
Okay.
yeah. But for example, the composition of carbohydrates.
I looked at the years and a couple new, but some are old. But I also just uploaded a ton and I feel weird that being old ones is like a recipe. I put a bunch on this.
No, it's all absorbable.
Allogenicity and protein modification. Which is like modifying systems for
Yeah, but you just told me it's going to snow 10 inches.
10 inches? I think Noor will get a snow date, but I'm not sure about.
Last year it snowed that much one day and everyone was big as. I was pretty upset about it.
Here, college or schools?
Oh, Nora was in school too.
Yeah?
I remember it vividly because I was upset. Oh, yeah.
So what time does it start snowing tonight?
Tonight at 18.
8? Okay. All right, are we ready to continue?
So
Huh?
when we decrease the pH and change the protein structure, and if we change back the pH, you said it's reversible reaction.
Well, okay, hold that thought. Don't take it word for word. You can reverse it. However, if the protein stays elongated period of time, at an isoelectric point or at a very high pH or a very low pH, you get irreversible denaturation. So if it stays, that's why, for example, we don't dry proteins at the isoelectric point. That means we're leaving them for a long time at that neutral pH. And then if you put the protein at pH 12 and leave it there for an extended period of time, you're causing irreversible denaturation that might lead to polymerization and then no way back.
So all the amino acid groups or peptide linkages are arranged in a certain way in the protein.
Yeah.
So when we reverse it back, will the same type of interactions be there? Which was before?
Not necessarily. So you might go from an alpha helix to beta sheet to more higher random coil. No, you might not necessarily go back to the original native structure, but you might go back to a compact structure. Yeah, like rather than an unfolded structure, it might fold back, but not necessarily the way it was folded originally. Mm-hmm. Yeah. So, for example, when we heat beta-lactoglobulin for a short period of time, it goes. Some of the alpha helixes become beta sheet, and becomes more thermally stable if you heat it again. Yeah.
Will that not affect any research studies that's going on? Meaning, they will have when adjusting a pH, they will have precipitated the case and brought it again.
Yeah.
So it would have a different structure.
It will have a different, yes, it will, definitely. There is no, in real life, there is no protein ingredient out there that is native form. Yeah, that is, no. The native form is in the cell before you break it and extract it. Yeah. Mm-hmm. But good question. All right. So, just briefly, I want to go over the importance of chemical reactivity, again highlighting the different functional groups. So we have the amine groups and the carboxyl groups that get ionized at different pH, so they impact the net charge of the protein. And the amine groups can also take part in Maillard reaction. Sulfidal groups, we talked about that. They are important in forming disulfide bridges. Sometimes it is wanted, other times it's not wanted in terms of the final application. Phenolic groups, in the case of tyrosine here, this is an ionizable group. So at high pH, it will become ionizable, and then it will also impact the protein net charge. Hydroxyl groups that will take part in post-translational modifications. We talked about that. And then thioether, which is in the methionine group. So also it can have a certain chemical reactivity that will break the bonds and make this a free sulfide group. Break the methyl group and make it a free sulfide group. Imidazole and guanine groups can also have chemical reactivity, and if you want to know more about the chemical reactivity, there is in Phenema, there is a table with the chemical reactivity of the different groups and under what reagents, with what reagents and conditions, what products, and what outcome you get. Okay, so here, for example, amine groups, you can have acetylation of an amine group or succinylation of an amine group. Acetylation is basically eliminating a positive charge where you put an acyl group at the amine group here. And with that, you are increasing the net negative charge of the protein. By blocking a positive charge, you're increasing the net negative charge of the protein. Succinylation, you're adding you're adding a negative charge, you're adding additional carboxyl group. And in this case, you're also increasing the net negative charge of the protein. In both cases, there's been application of acetylation and succinylation to increase the solubility of a protein or to enhance the emulsification properties of the protein. We'll talk more about that when we talk about protein modification towards the end of the semester. Phylation, you can potentially add a thiol group to a protein residue. In this case, you eliminate the positive charge and you introduce the thiol group, which may take part in disulfide linkages. Sulfidyl group reaction, you can have oxidation to enhance the sulfide formation, or you can block a sulfidyl group so that you eliminate the SH that can react and cause polymerization. Sometimes you don't want to have active thiol groups, so you can actually block it. So there are chemical reagents that will allow you to do that. And some of these reagents, we have assays in the lab, for example, to determine total sulfidyl groups and total surface sulfidyl groups. So this is based on the blocking characteristics here, where you reacted with the reagent and you block the sulfidyl group, and then you measure the absorption of that product that is formed. Like in this case, this is a phenolic product or a ring product that would have an absorption or is a chromophore is the word I'm searching for. Chemical reactivity is also important when we want to quantify. So if we want to determine amino acid composition, oftentimes of a protein, what you need to do is you break down all the peptide bonds by hydrolysis with an acid or a base, and then what you do is you end up with amino acids, free amino acids, and then you want to quantify those. So these free amino acids, not all of them absorb light, only tyrosine, tryptophan, and phenylalanine. So in order for you to quantify them, you can react them with the reagents such as ninhydrin, and you can follow here the reaction of a formation of a chromophore that you can measure the absorption of at 570. For proline and hydroxyproline, we measure at 440 nanometer. So often you do that after column separation. You have your amino acid, you separate them by column, then you react them, then you measure absorption, and you can quantitate the composition of each amino acid as it comes out of the column. Reaction with ophthaldehyde, this is a very common method that we use based on the fact that the OPA reagent reacts with primary amines. When it reacts with a primary amine, it gives you a fluorescent compound, and you measure absorption at 380, but fluorescence at 450. Oftentimes, we measure fluorescence. Two applications for this. One is if we want to determine extent of hydrolysis, if we're hydrolyzing protein, and we want to determine how many peptides did we break. The more peptides we break, the more primary amines we are releasing, right? Then the more primary amines are available to interact with our OPA reagent. So usually we run a standard curve and we quantitate that way and use an equation to calculate what is known as degree of hydrolysis, which we'll talk about when we talk about hydrolysis later on. Another application for this is if we want to determine blockage of primary amine. So if I want to determine blockage due to Maillard reaction, for example, oftentimes I have lysine as a standard, and then I would measure the free amine in a non-treated protein and a treated protein. Then I will know that if my reaction goes lower, is reduced, that means some of my primary amine got blocked and no more interacting with the OPA, and I can calculate percentage of blocked amine groups. Another reaction is also an interaction with the fluorosamine. Again, it's another type of compound reacting with the primary amine and giving a compound that would fluoresce, measure fluorescence. Okay. Any questions? Okay.
Is it normally done in intact proteins too? You see, it's not.
Yes, it's done in intact protein, not a primary amine of an intact protein. Yeah. It doesn't have to be a hydrolysis or a free amino acid. Yeah, definitely. That's what we usually do it on a protein that is intact, and if we hydrolyze, we do it again to see how many free amine we released. And if it's an intact protein that we processed, we determine how much we had free amine versus blocked amine using a lysine standard curve. All right. Now that we are experts in amino acids, we start building the protein. Okay? So, peptide bond. We start with the very early explanations of a peptide bond, which is a bond between a carboxyl group and amine group. So this is what forms a peptide bond. So the reaction is a condensation reaction. So we release water once it's formed. Once the peptide bond is formed, 1 molecule of water is released. And in nature, we have the L configuration or conformation where the amine group is left and the carboxyl group is the right. And then this we call amino terminus, and this is carboxy terminus or N terminus. If you hear N terminus, that means the amino terminus, means the same thing. You will later hear about N-terminal sequencing, for example, which is a method to determine amino acid sequence within a protein. And it's called N-terminal sequencing because the sequencing starts by breaking off an amino acid from the N-terminal site. And that's why it's called N-terminal sequencing. Okay. All right. So the primary structure, so we have primary, secondary, tertiary, quaternary. Primary structure is simply the linear sequence of amino acid. So when the DNA have the sequence and the RNA is forming the proteins, then we have the sequence of the amino acid, and that is your primary structure. So the average molecular weight of one amino acid is 135. Obviously, it's just the average. And most proteins are in the range of 20 to 100,000 Dalton, or we can say 20 kilodalton to 100 kilodalton. This is also a very common unit. Of course, there are proteins that are smaller, like alpha-lactalbumin, for example, in milk is 14 kD. Soy protein can form a quaternary structure up to 300 kD. So this is really just the range. And the larger the sequence, obviously, the higher is the molecular weight, right? So the linear sequence and length, the length determines the molecular weight. So both linear sequence and length, what do they impact?
The folding and then how it turns into the secondary structure and then ultimately the structure.
The hydrophobicity.
So structural configuration and hydrophobicity, and the location of the hydrophobicity, more on the surface, more inside. And with the structure comes the function. Okay? So if a protein is more hydrophobic on the surface, it won't like water as much. If the protein has a good balance of hydrophobic and hydrophilic on the surface, then it will emulsify really well. If a protein has low hydrophobicity on the surface, then it will be highly soluble, like beta-lactoglobulin. So structure impacts function. Another thing with the the higher the molecular weight of a protein, the lower is the solubility as well. So that is another impact of length. And the higher the molecular weight of protein, the better the tendency to form a gel, a three-dimensional matrix. Okay. So I'll explain few concepts and few angles here because it will relate to how the protein folds later on. Okay? So if I take the peptide bond, which is the omega angle, it's mostly fixed at around 6 degrees. And why is it fixed and it has minimal rotational freedom? The reason it has minimal rotational freedom is because it acts as a partial double bond. It has a partial double bond characteristic. So the electrons here and the electrons from nitrogen and oxygen, sometimes this bond breaks here and the electron from the hydrogen is borrowed here. This becomes a positive charge and this becomes a double bond. So it is kind of interchangeable between a single bond and a double bond. So because of that, it doesn't have a rotational freedom. Okay, so that is one bond. Oh, which is illustrated here. I forgot that I had these illustrations for the double bond. All right, and then we have two more important angles. The phi and the psi. The phi angle and the psi angle. So the phi angle is the rotation of the bond between the nitrogen and the alpha carbon, or the amine group and the alpha carbon. And the psi is between the carboxyl group and the alpha carbon. Right? And then the green here is your R group. Okay? This green demonstrates the R group. These two theoretically have freedom of rotation and stretching and bending. They're not restricted like the omega angle. Now, that is, theoretically speaking, they're not restricted. But the R group imparts some form of restriction through steric hindrance. Okay? So the type of the R group impacts how these bonds are going to rotate, stretch, and bend, and accordingly impact how the protein is going to fold and what type of interactions will happen once that protein sequence folds. It depends on how it folds, what's this distance between one functional group and another. Can I form hydrogen bond now? Can I form a hydrophobic interaction? Or what kind of bonding can be formed upon the bending of that bond? Okay, so this is just basically telling you that the peptide backbone is a series of continuous sequence of C alpha here to C alpha here, in between a carboxyl group and amine. Okay, so this the backbone is really a continuous series of these groups. That's all it's saying. Oh, and this is, I already said, have rotational freedom, 360 degrees, but theoretically, the rotation freedom is determined by the R group based on the steric hindrance of the R group, how big it is, what functional groups it carries, and the rotational freedom affect the structural configuration, how it's going to fold, what type of bonding is going to form based on the distance between the functional groups. to remind you of proline and why we call it a structure, secondary structure breaker, because the phi angle or the bonding here is really very much restricted. There's not much flexibility because of the R group bonded to the amine group. And that's why it really doesn't bend. So if we're forming a alpha helix, for example, the protein is forming alpha helix, and then there's a protein. It can't fold anymore. It breaks. So now I have random coil. Then the sequence continues, and I can form alpha helix or beta sheet, and then there's a proline. Secondary structure breaks. Okay? Because it doesn't fold the way it's supposed to fold to form alpha helix or beta sheet or beta turn. There are two different configurations of the bond. So you have the trans configuration, which is the more stable, and then you have the cis configuration, which is less stable, because if you look at the cis configuration, you have the two carbon alphas from two different amino acids. So your R group is somewhere here, and then there's so much of steric hindrance. That's not a configuration that is preferred. The cis configuration, the R group is here, the R group is here, and there's not much of a steric hindrance. That's more stable and more present in nature. With the exception of a proline, because of its cyclic nature, you can have both cis and trans configuration. And because of that, it's found more in cis than any other amino acid. So that's all what this is saying. Okay. So once the peptide bond is formed, can we break it? Yes, of course we can break it. We can break the peptide bonds either by chemical breakage or enzymatic breakage. So the chemical breakage often requires conditions either acidic or basic with heat. So you want, because it's a covalent bond, it requires really high energy to be broken. So because once a peptide bond is formed under normal conditions, there is, you know how every reaction has an equilibrium constant, right? In the formation of a peptide bond, you have an amino acid plus an amino acid gives you a peptide. At equilibration constant, you have the peptide going backwards, but it's really high. That means it requires really high energy for it to actually go backward. Okay? So in order to break the peptide bond, we need some sort of a force and energy. And that's in the form of heat, the presence of acid or base. So when we want to determine protein composition, we have to apply hydrochloric acid mostly and heat for a really long time at really high temperature, so we ensure that every peptide bond is broken. But whenever we send, let's say, a sample for amino acid analysis, or you want to do amino acid analysis in the lab, we can never determine all of the amino acid by using one method. Because, for example, acid hydrolysis really degrades tryptophan and cysteine. So you have to prepare the samples by acid hydrolysis, prepare them by base hydrolysis, and then measure at different rates or different time points so that we can determine and quantitate accurately most of the amino acids in our sample before they get degraded or destroyed. Yeah, because also here under acidic or base conditions, asparagine and glutamine are converted to their aspartic acid and glutamic acid by the release of an amine group or ammonia. All right, we can break peptide bonds by enzymes, and there are many enzymes out there, proteases and proteinases, that are out there that would break peptide bonds, and they really differ by their specificity. That means their preferred site of action. Where do they cut? Some some enzymes are highly specific, like trypsin, for example. It cuts after the carboxyl group. So see this faint line here? I'm demonstrating that it's cutting after the carboxyl group of a lysine or arginine. So that's why it's commonly used in MS analysis, right? So Vaidi were asking me about that the other day. So because we know where it cuts, there are libraries that tell us, can identify the type of peptides that can be generated after using trypsin. So when you cut, you can look at database and identify the peptides generated. Other enzymes are non-specific. They're mostly digestive enzymes. That means they can cut most peptides. They can cleave most peptides. Chymotrypsin is not very specific. It cuts at different amino acids. Subtilissin has very limited specificity. That means it really cuts most peptides. So it really depends. Do you want to hydrolyze randomly, or do you want to use enzymes? For example, alkylase cuts at aspartic after an aspartic or glutamic acid, I believe. So oftentimes they use alkylase to generate peptides that will form aggregates or prone to gelation. Because after they cut, after a hydrophilic amino acid, they tend to generate hydrophobic or slightly hydrophobic peptides that would form aggregates. So it really depends on what application. You can choose different enzymes. There's so many enzymes to choose from and so many different specificity. Oftentimes it's trial and error. If you don't know everything, you just try and see what works. Yeah. All right, so moving from primary to secondary and tertiary structure. So why won't the protein stay as a linear strand? Why does it fold? Lisa? That's one reason, but there's also something else.
Is it more stable when it falls?
Yeah, why?
The charges?
Huh?
The charges on the...
It's more stable when it folds. What makes it more stable when it folds? Huh? Less energy. What makes it have less energy, free energy, is the bonding. Okay? So when you form the linear chain, okay, so there's so much free energy, so much rotation, so much stretching and bending, and steric hindrance, so steric strains. So it's really, and it's strained because they want to rotate, and then there is restriction by the R group, and there is the stretching and bending. With stretching and bending, you have high energy, very unstable state. And then what happens, hydrophobic interactions brings the protein to fold. And when they start coming together and the residues are close to each other, they start forming bonding. And each bond contains part of that free energy. And the more bonds are formed, the more free energy is contained. That brings us to enthalpy and entropy. You like this, right? Mm-hmm. So enthalpy is the energy that is contained within the bonds. Entropy is the chaos. Okay? So the more you contain the energy, the less entropy you're going to have. Okay? So when delta G, for instance, is negative, that means you have a spontaneous denaturation of the protein. Because something has happened that the entropy went way up, the change in entropy increased, and this became negative, then you get spontaneous unfolding of the protein. We'll talk more about what causes this to happen. But think about it for now is when the bonding happens, we are increasing enthalpy, we're increasing the change in enthalpy, and decreasing entropy. So we're going from a least stable, which is the primary structure that has so much free energy, to a more and more stable structure. Secondary structure contains a lot of the energy, but we still have more energy to contain, and we form tertiary structure. Sometimes with tertiary structure, this is not stable as it is. Some proteins form quaternary structure, like the casein in my cell, or the fibrillar protein in meat. So you form quaternary structure, or the soy protein is a quaternary structure, whereas whey protein is mostly monomeric protein, like that. Sometimes they can form dimers and octamers depending on the pH of the system. So let's talk about the role of hydrophobicity and water in the folding of the protein. So it plays a major role in the folding, and how is that? Like I said earlier on, these groups in the primary structure, they don't want to associate with water. So what they start doing is they start coming together to hide from water. They start interacting with each other. So now what happens is when these are interacting with each other, they kind of folded the protein. So we have a carboxyl group here and a hydroxyl group here. They can form a hydrogen bond. So electronegative atom with hydrogen bonded to an electronegative atom, you form a hydrogen bond. Right. So when you're forming hydrogen bond here, you're no longer forming hydrogen bond with water. So the water is pushed outside of the protein. Okay? So now we're having hydrogen bonding happening within the protein, and the water is outside. So you have less hydrogen bonding with the water. And that's why secondary structure is mostly stabilized by hydrogen bonding. So what drives, okay, I might ask you two questions on the test. What drives the folding or the formation of secondary structure in a protein versus what force stabilizes the secondary structure of protein? What would be your answer to each? Yes, Lisa?
Hydrophobicity drives it, and then hydrogen bonding
Stabilize it. Thank you very much. Did you get that, Rachel?
Yes, I did.
Yeah. I know you're taking notes. Okay. All right, so what I'm doing now is I'm going to introduce the different bonding that can occur within a protein. Then I'm going to build the structure from primary, secondary, tertiary, and quaternary. First, let's look at the different bonds that can form within the protein. So, dipole interactions, which are very weak interactions, also can be known as van der Waals. You might know them as van der Waals. So the atoms that are neutral, or the groups that are neutral, they can interact when they are very close to each other with a distance of 6 angstrom, right? I was just thinking what you call that unit. Okay. They are weak bonds, but there are a lot of neutral elements that can interact within the protein, so they are additive. That means they can contain potentially a lot of free energy, because there is a lot of them. They're weak but additive. So they contribute to the stabilization of the structure of the protein. Okay, hydrogen bonding. So it's an interaction between a hydrogen atom bonded to electronegative and another electronegative element. So there are a lot of potential for hydrogen bonding. A lot of the hydrogen bonding can occur between groups such as threonine, serine, aspartic acid, glutamic acid, have a tendency to form hydrogen bonding. And here the distance is 2.9 angstrom for it to occur, for the hydrogen bonding to occur. Electrostatic interactions, so here, by its definition, so it's an interaction of opposite charges. So you have a positive and a negative depending on where they are in the sequence and if they are in close proximity. And oftentimes charged amino acids are involved with ionic or electrostatic interactions. So these are the 3 basic amino acids and the 2 acidic amino acids. And here's the question, what's the effect of water? All right, so because these ionizable groups have a tendency to like interacting with water versus interacting with each other, they tend to be on the surface. So, for example, take lysine. The amine group of lysine is really not directed to a carboxy group. It's mostly to the outside. In the presence of water, it prefers interacting with water. So while there is some ionic or electrostatic interaction within the protein itself, they're mostly on the surface and they interact with the water. All right, hydrophobic interactions. So these are another major force during stabilizing the protein as well as driving the folding structure, folding of the protein. So they play 2 roles, folding and stabilizing, because they're driving the folding and they are contributing to take up of energy and reducing the free energy as well. So and the reason why they interact with each other is simple. They don't want to interact with water and they don't want to interact with polar groups. So they end up interacting with each other. Disulfide linkages, which are the strongest bonds and they hold the most energy. So, like I said, the more disulfide you have within a protein, the more stable is the tertiary structure. And sometimes you have disulfide linkages between 2 subunits to form a quaternary structure, such as in soy protein. Glycine subunits form disulfide linkages. So the quaternary structure of glycine is stabilized partially by disulfide linkages. So they stabilize tertiary structure and may also stabilize quaternary structure. All right, this is an important table. Put 3 stars, 5 stars, 6 stars. We need to know this information because there are so many applications, whether for analytical purposes or for food application. We need to know what drives these interactions, what makes them stronger, what makes them weaker. As we design our analytical experiment or as we process a food product, we need to know what causes interactions or reduces interactions. All right, so this is a really important table. Okay, so these are the different types that we talked about, and their order, kind of in the order or not. They're not in the order of highest to lowest because this should have been the second. Never mind. Covalent bonding it contains the highest energy and it requires the highest energy to be broken. Okay? So within a protein, the functional groups, if you have cysteine groups, you have the potential to form disulfide linkages. Some proteins don't necessarily have cysteine in them, such as casein proteins. There is probably 1 double caseins in kappa caseins or something like that. So some proteins are really high in them, like alpha-lactalbumin is high in sulfur-containing cysteine. Also, egg proteins is high. So it really depends on the composition, and depending on the composition, you might have a little or none or several disulfide. How do we break them, disrupt them? Reducing agent. So we'll talk about the use of reducing agent in applications such as gel electrophoresis and why it's important and what does it tell us. So reducing agents such as mercaptoethanol or beta-mercaptoethanol, cysteine itself can act. So you can add cysteine and it will like free amino acid cysteine, and it can be a reducing agent. Sulfides are reducing as well, and there are several other DTT. I'm not gonna even try and say it. I know it's DTT. Can you say it, Rachel?
Diethyl.
Right.
Okay, good. Last one. All right. Next, hydrogen bonding. It contains about 8 to 40 kilojoule per mole. And this is the distance. I'm not really too concerned that you know the distance as much as you know approximately the order of energy, not necessarily the amount, and what functional groups are involved, what are the disrupting solvents, and if there is any enhancing conditions. Okay.
Is it the energy to form or is it the energy to break the bond?
I mean, it's the energy that's contained within the bond. So obviously you need that much energy or higher to break it. Yeah. That is actually the energy contained within the bond. So when it's formed, it's reducing the free energy by this much. Okay. So hydrogen bonding, so we said it's between specific groups, amide, hydroxyl, phenol, and carboxyl groups. So we can break hydrogen bonding with urea, for example, or with detergents, guanidine, hydrochloride, and heating. As you increase the heat, the hydrogen bonding decreases. Think of collagen and formation of gelatin. So when you have collagen in its native form and then you heat it, what happens is you are breaking hydrogen bond because collagen is mostly stabilized by hydrogen bond. Okay? So when you heat it, you are breaking the hydrogen bonds, and then when you cool it, they're going to form, but not in the same way they were originally, and then you form gelatin. Okay? And it's reversible because gelatin also, if you put in water and heat it, it will solubilize. And then also, when you cool it down, it will form hydrogen bonds again and solidify. Okay, so cooling enhances hydrogen bond, heating reduces hydrogen bond. Hydrophobic interaction between any residues with long aliphatic or aromatic side chains. So you can break hydrophobic interactions with detergents such as STS, sodium disulfide. Organic solvents, you can break hydrophobic because your hydrophobic residues would want now to interact with the solvent. So if you have hydrophobic residues inside in the interior moiety of the protein, then they sense the presence of organic solvent, so the protein opens up so they can interact with the organic solvent. Heating, as you heat, you enhance the formation of hydrophobic bonding. Cooling actually does the opposite. So I have a question later on in the daily section. Why would beta-casein leach out of the micelle in cold milk? Remember that question when we talk about the structure of beta-casein. So anyway, cooling reduces the hydrophobic interactions, whereas heating increases it. Electrostatic, so any charged groups, obviously, and you can disrupt it by increasing the salts, because now instead of interacting with each other, they will interact with the salt ions instead. Or when you change the pH, you will change the ionization state. So you either protonate or, you make protonate, so you might lose the charge on the carboxyl group, for example. So changing the pH either high or low may disrupt electrostatic interactions. So van der Waals, if they are in near proximity, they are formed, and they're instantaneous. They can form, and they're weak, but they're additive. So one last slide before we quit for today. I just want to again restate the concept of the free energy. So basically when it's primary structure, there's a lot of free energy, and then when the bonds are formed, you contain the energy in the bonds, and the chaos is reduced. However, if something induces bonds breaking, like few bonds of hydrogen bonding, for example, so here in this case, 20 to 85, change of 20 to 85 kilojoule per mole is equivalent to 1 to 3 hydrogen bonds. So if we do anything in the process that causes the breakage of 1 to 3 hydrogen bonds, will increase tremendously the delta S, and that will cause a chain reaction of unfolding. We broke hydrogen bonding, the protein opened up, so now it's no longer closed for ionic interaction, no more closed for hydrophobic interaction, so it's kind of a chain reaction and the protein unfolds. Okay. And one last thing here, when this summation side, this is meaning the change in delta G of all of the interactions, of all of the bonding within the molecule itself. Okay, I can stop here.